Hello, this is Todd Frazee, and this is ADVM 12, lecture on Runout by Todd Frazee. Hey, introduction. In this lesson, we will explore how to control functional relationships of surfaces as they rotate around a datum axis using the runout geometric control. You will learn to describe two types of runout tolerances, circular runout and total runout, and understand their distinct applications and benefits. Through interpretation of drawings, you will visualize how each runout tolerance is measured and how to apply these tolerances to circular features and face surfaces effectively. The lesson will also cover how to specify tolerance using common datum feature references and how to limit the area of application for greater control, and how to apply how to apply runout tolerances to tangent planes and features within assemblies. Okay, objectives. By the end of this lesson, you will be able to describe two types of runout tolerance, complete an interpretation drawing showing how each of the runout tolerances is measured, apply both types of runout tolerances on circular features and face surfaces, specify runout tolerances using common datum feature references, limit the area of application for runout tolerance, apply a runout tolerance to a tangent plane, and apply a runout tolerance to a feature in an assembly. A runout. It's a surface variation that occurs relative to the axis of rotation. The tolerance specifications define the amount of runout variation permitted on the surface or tangent plane. The tolerance symbol indicates circular or total runout. Both types must include one or more datum feature references. Okay, so circular runout is a surface variation at each circular element part. And the tolerance value is not limited by the size of the item. Each measurement of multiple elements is elevated separately, and the largest reading on the circular runout for the part is what you'd record for inspection. So here we have a cylindrical part. It's spinning and it has 3 different diameters on it. You would have to measure in one spot on each one with the indicator, if it was called that way, and measure how much it deviates on that indicator would be your runout as it's spinning. Okay, circular runout, feature control frame. The circular runout tolerance symbol first, followed by the tolerance value. So a circular runout is just a single arrow pointing diagonally. And the diameter symbol is never included. It's implied. The thing you're checking is round. And it's always applied at regardless of feature size. And one or more datum feature references are needed. Okay, so we got a couple examples there. You got your tolerance is how much the indicator moves. RFS, we don't have to worry about modifiers. And it's always at regardless of material boundary as well. So no modifiers to worry about, the complexity of those. But they are very difficult to hold. In the second example, we've got A through B. It's common datum feature plane datum, and the second one has a primary and secondary datum reference. Okay, circular runout applied to a cylinder. Checked by multiple separate indicator readings per feature. Internal or external features could apply, and surface control relative to the axis of rotation. And the tolerance zones applied along the full extent of the feature. Okay, circular runout applied to a non-cylindrical surface of revolution. Applicable if the feature includes circular elements centered on an axis of rotation and variations measured with a dial indicator perpendicular to the surface you're measuring. Okay, so we have a cone and we have a semi-spherical shape. So you have to mount the indicator. You have to have a lathe or a device that can spin the thing, and then you take your indicator reading at individual points. Okay, circular runout applied to face surfaces. Circular elements can exist on the face surfaces of external or internal features. Controls the amount of allowable wobble when the part rotates on its axis, but it does not control the shape of the overall surface. You just have to hit a couple areas, and as long as the indicator's not running out, it's not controlling that spherical radius in this case is plus or minus 3 thou. Okay. Okay, limited tolerance on application. So there's a way you can limit the area that you want to be held to the tolerance. Only specify a needed level of control to avoid cost. Runout tolerances control entire surface applied to unless otherwise noted. And the area of limited application indicated with supplemental geometry as shown in the top, where you have a model and a chain in orthographic views. So they chopped off the geometric frame in the orthographic view in the graphic, but you would show a chain line and then call your run out to that chain line, and then you would have your dimensions of where that chain line zone is. If it was in a model, you'd have to do some supplemental notation that comes up in the annotated model. Okay? It would show the zone limits. Okay, axis of rotation. All runout tolerances must include one or more datum feature references to establish the axis of rotation. The entire surface, partial surface, or datum targets could be used. Datum feature selection based on manufacturing and inspection process. And manufacturing and inspection process is important to plan ahead size, proportions, and relative locations of the datum features as well. Okay, here's an example of a single datum feature callout. Okay, it's referencing one datum feature, often adequate because your application is to a cylindrical part that defines the center line. And the proper datum feature selection is essential for verification and low production costs. So I've worked recently with a local manufacturer that's struggling to make a part because they call the run out to a face that has a loose tolerance on it as opposed to the center axis of the part. And so they're having to hold this 90-degree face super tight tolerance in order to control the run out. Okay, common datum features. 2 or more features used to establish a single datum, indicated in feature control frame with a hyphen between the datum feature reference letters, and defined by referencing 2 or more datum features at the same precedence level. A common datum features for external features. The axis of rotation established by 2 features. Both datum features use simultaneously to establish the datum axis. So in this case, they're using 2, so it's B and A, and you put a dash in between to indicate that. And again, semantics of how datums are called out, you notice they replace a leader line or right on the center of the dimension line. That implies center line. There is no need for a dimension going from the edge to define where center is. Okay. Common datum features that are internal. Coaxial holes may be used to establish the datum axis. So that'd be holes in line with each other. Possible to use non-functional variations as datum features. And consider accumulation of tolerances between non-functional and functional features. Okay, so common datum features, if you're using targets, when specific locations on a feature are used to establish the datum axis. A functional datum feature may be large enough to make contact with the whole feature is impractical, or when irregular features require specific location to be located. So this is, you know, your machine, you have to hold it in some sort of chuck to spin it, it's going to define where that's going to be. And you might have zones, target zones on where the datum has to hold this item. So for example, in this case, it looks like datum A3 and B3 are points on the inside of this cylinder, and then you've got another one that's opposite of that. So you're hitting this. This needs to be held in 3 places on the. Oh, it looks actually. I'm sorry. It's the outside diameter. Okay, so that might be the 3 jaws of a chuck. Okay. Okay, run out reference to a primary and secondary datum. Some applications require a second datum feature to stabilize the part. Must include one datum axis and one datum plane. Okay, so we've got, it's called the A, which is a cylinder, and B is the plane, the back of this cylindrical part. And whether the axis or plane is primary depends on the design function of the part. A total runout. This is the second type of runout. There's only 2. There's circular runout and total runout. It's a variation across an entire surface of a part or relative to an axis of rotation. And allowable form, orientation, and location of cylindrical or flat surface elements relative to the axis of rotation are controlled. So with circular, you're not controlling the surface. With total runout, you are. The tolerance value is not limited by size limits, and FIM caused by surface variations across the entire feature, the total runout variation. So FIM is your indicator reading. Okay, so total runout control frame. Okay, total runout symbols first. Followed by allowable tolerance. And so it's 2 arrows at 45 degrees that are hooked together by a line. So it's showing your runout needs to be over a surface. And it's always, the diameter symbol's never applied. Okay. And it's always regardless of feature size. So no modifiers. And datum feature references are made in the same manner as circular runout, but the way you check it, you have to account for the entire surface. And it's always applied regardless of the material boundary. Okay, total runout applied to a cylinder. Internal or external features. The FIM must be equal to or less than the specified tolerance. So again, FIM, I need to fix this slide. It's an indicator reading, your total indicator difference on the needle. So in this, you'd have to put the indicator most likely in the machine like a lathe and be able to run it across the entire surface as it's spinning. Okay, total runout applied to face surfaces only applies to one surface indicated, and opposite face of the part is not controlled by the tolerance. Okay, and total runout applied to the tangent plane, tangent to one surface or multiple coplanar surfaces. The numbers noted when more than one is included in the requirement, and the extent of the plane and distance from the axis of rotations to the furthest point on the tolerance surface needs to be noted, and the profile tolerance to control tangent plane feature surfaces relative to the datum axis. Okay, combined effects of size and runout tolerances. Runout may be larger than the size tolerance. The size tolerance may be larger than the runout. Okay, one or the other. That's allowed because it's regardless of feature size. Runout variation may occur on perfect form feature. And feature must meet both size and runout requirements. So one doesn't trump the other. Okay, here's an example of a small size tolerance on a large runout with a large runout tolerance. So we're holding the outside diameter of this feature 1 inch plus or minus 5 thousandths, but it's allowed to wobble as long as it measures that size up to 15 thousandths. Okay, so our allowable indicator movement is allowed to move 7.5 thousandths in either direction of what would be neutral. Okay, here's a large size tolerance example with small runout tolerance. So we're holding this plus or minus 10. The cylinder has to be held that, but our FIM on the outside diameter needs to be within 6 thousandths of movement. Okay, so you're only allowed 3 thousandths of wobble per side. Okay, runout applications on assembly. Circular runout may be applied to assemblies. Establishes a tolerance requirement relative to the axis of rotation. So in this case, it's a motor with a pulley on it. And the axis of rotation is constrained in rotational degrees of freedom relative to the datum reference frame. And the reference datums do not constrain translational degrees of freedom. Okay, so it's only on the surface itself. All right, that's it for this one. Short and sweet. No MMCs or MMBs to talk about. But in summary, in this lesson, we've explored how to control the functional relationships of surfaces as they rotate around datum axes using the runout geometric control. You learned to describe the two types of runout tolerances, circular runout and total runout, and understood their distinct applications and benefits. Through the interpretation drawings, you visualized how each runout tolerance is measured and how to apply these tolerances to circular features and face surfaces effectively. The lesson also covered how to specify runout tolerance using common datum feature references, how to limit the area of application for greater control, and how to apply runout tolerances to tangent planes and features within assemblies. Okay, in conclusion, by the end of this lesson, you were able to describe two types of runout tolerances, complete an interpretation drawing showing how each of the runout tolerances is measured, apply both types of runout tolerances on a circular feature and flat surfaces, specify runout tolerances using common datum feature references, limit the area of application for a runout tolerance, and apply runout tolerance to a tangent plane, and apply the runout tolerance to a feature in an assembly. Thanks a lot. This concludes this lecture, and we'll catch you on the next one.